Hi, thanks for joining me. Today I've got another non-standard proof for you. Today I'm going to be proving that the square root of 2 is irrational. Now I've already proved this result a bunch of times on the channel, so I'll leave a link in the description below to a playlist I've made of non-standard proofs, and in there you'll find a bunch of non-standard proofs to the irrationality of root 2, and here is another one to add to the collection, and this one involves geometry. Let's get stuck in. Okay, so as with most proofs of the irrationality of root 2, this is going to be a proof by contradiction. So we're going to start by supposing for contradiction that root 2 is a rational number. So root 2 equals a over b, where a and b are positive integers, so natural numbers. And we can also assume, without loss of generality, that the greatest common divisor of a and b is 1. So a and b are co-prime, they share no factors, because if they did share a factor, well then we can just cancel them down from the numerator and denominator until we get two numbers which do not share a factor, so are co-prime. And also what this kind of subtly tells us is that this is the smallest choice of a and b. If there were a smaller choice of a and b to write root 2 as a sort of ratio of, well then that would kind of correspond to this pair of a and b sharing a factor. And that's not possible because we're assuming that they are co-prime. Okay, the next thing we're going to do is draw a right angle triangle, and it's going to have base length b and height also b, like so. And then, of course, just by Pythagoras Theorem, its diagonal length, that guy there, is going to be the square root of b squared plus b squared, which is 2b squared, like so. Well then, if we just look at what we have here and square both sides, we get that 2 is equal to a squared over b squared. So, of course, 2b squared is just a squared. So this thing here is just the square root of a squared, which, of course, is just a. So we get this right angle triangle here, like so. And then the next thing I guess we want to do, well, essentially what we're trying to do is construct another right angle triangle with integer lengths that's similar to this triangle, except the side lengths are less than b, and this side length here would be less than b, and this side length here would be less than a, but all of them would be integers, but then that would kind of contradict this guy here because we've chosen a and b to be as small as possible. And the way we're going to construct that right angle triangle is we're going to start from this point here, and we're going to draw on a circle with that center and radius b. So it's going to pass through this point as well, and it will do something like that, but what we're interested in is what it does up here. It will look something like that, but it's going to pass through this point here like so. So this is a circle and it has radius b. Okay, and notice that if I draw on the tangent to this line here, to the tangent to the circle, sorry, at this point here, it's going to look something like that, and it's going to intersect this guy there, and this thing here will be a right angle, just by a pretty basic circle theorem. Okay, but notice that this length here is a minus b, because the whole thing there is a, and this length there is b, so this what's left must be a minus b. And similarly, this length here is a minus b. Okay, so we've got this length here being a minus b, this length here being a minus b, and in between we've got a right angle. So it's looking the same thing as this guy here, or a similar triangle to this guy here, because it's got a right angle, and then the two lengths either side are integers, that's b and b. So the last thing we need to do to arrive at our contradiction is check that this length here is an integer. Okay, so let's just quickly go over what we've done. We've constructed this new kind of right angle triangle, which we know is similar to our bigger right angle triangle by the side angle side, I guess, because this side here is is in a ratio of b over a minus b to this side here. Similarly, this side here has the same ratio to this side here, and this angle is the same in between. So what we're doing is, if we can show that this remaining length here, which corresponds to this long length here, if we can show that that is an integer, then we'll arrive at our contradiction, because we found another right angle triangle which is similar to the one before, except now it has integer lengths, but those integers are smaller than the ones we started with, and that's a contradiction because we assume that a and b were as small as possible. Or another way of thinking about it is, we can kind of proceed by infinite descent and find a ratio of a and b which is smaller than a and b, and then keep going down and down and down, and we can do this process forever. However, we know that that's impossible because the positive integers are bounded below by 0. But of course, what we still need to do is check that this length here is an integer. Well, just by Pythagoras Theorem, it's just the square root of 2 times a minus b all squared, like so, which of course is just root 2 times a minus b. But root 2 is just a over b, so this is just a over b times a minus b, like so. And then this is just a squared over b minus a over b times b, which is just minus a. So a squared over b we need to show is an integer, but notice if we just go up to this equation here, we get that 2 is equal to a squared over b squared. So just multiplying both sides by b gives us that a squared over b is just 2b. So this thing here is just 2b minus a, and everything here is an integer, so this thing is an integer, so this side length here is an integer, and we've arrived at our contradiction. I hope that has all made sense. It's another nice proof, geometric proof this time, to the irrationality of root 2. I hope you have enjoyed this video. Thanks for watching. I'll catch you in the next one. Have a great day.